Okay, let us understand what are buffer solutions and how do they act to resist the change in pH in aqueous solutions. First of all, we have to define what is a buffer solution. This is the solution whose pH does not change appreciably. Number one, on keeping over time. That means you can store these solutions without any appreciable change in their pH. Their pH does not change on dilution. That means you can add water to them without having any change in their pH. Their pH does not change on addition of small amounts of strong acid or strong base. Okay, why and where do we need buffers? Generally, these buffer solutions are used in biological or physiological experiments where pH must be maintained around the pH of the human body. So all these biologists who are carrying experiments in vitro generally has to maintain the pH of their experiments to physiological pH. In industries also, we need buffer solutions such as cosmetic industry, pharmaceutical industry, where pH is very important in making such products. Now we have different types of buffers. Mainly, we have three types of buffers: acidic buffers, whose pH is below 7, basic buffers, whose pH is above 7, and neutral buffers, where pH is equal to 7. Now, what are the constituents of these buffers? What are these buffer solutions made up of? Now, depending on whether it is an acidic, basic, or neutral buffer, we have different compositions. An acidic buffer solution consists of a mixture of a weak acid and its salt with a strong base dissolved in water. For example, we can take a weak acid such as acetic acid and its salt with a strong base such as sodium acetate. So we have the composition of an acidic buffer as acetic acid and sodium acetate dissolved in water. Because we have these two constituents in the mixture, the reaction that are taking place in aqueous solution is the dissociation of acetic acid, which is in equilibrium with the undissociated and dissociated acetic acid, and the sodium acetate, which is a strong electrolyte. As it is a salt, all salts are strong electrolytes. So this being a salt will be completely dissociating into water in its constituent ions, that is acetate ions and sodium ions. Okay, so we have these two reactions that are taking place in aqueous solution in acidic buffers. In basic buffers, basic buffer consists of a weak base and its salt with a strong acid dissolved in water. For example, we can take a weak base as ammonium hydroxide and its salt with a strong acid as ammonium chloride. That is, the composition of a basic buffer is ammonium hydroxide and ammonium chloride as one of the examples. Now, with these two components present in water, the reactions that are taking place are ammonium hydroxide becomes in equilibrium with the ammonium and hydroxide ions, that is the undissociated ammonium hydroxide and the dissociated ammonium and hydroxide ions. And ammonium chloride, being the strong electrolyte, will be completely dissociated into ammonium and chloride ions. Okay, so this was the composition of a basic buffer. And we have neutral buffer, which is not a mixture, but it is made up of only a single constituent, and that is a salt. And this salt must be a salt of a weak base and a weak acid dissolved in water. For example, ammonium acetate. Ammonium acetate is a salt which is made up of weak acids such as acetic acid here and weak base, which was ammonium hydroxide. When acetic acid and ammonium hydroxide react, we get ammonium acetate. Okay, when this ammonium acetate is dissolved in water, this will be 100% ionized because, as I said, all salts are strong electrolytes. So ammonium acetate, being a salt, will be completely ionized into its constituent ions. However, these constituent ions are of weak acid and weak base. So this in turn will form an equilibrium between the undissociated acetic acid and the dissociated ions. Similarly, ammonium ions will also form an equilibrium with the undissociated ammonium hydroxide and ammonium ions. So this is the constituent of a neutral buffer, that is only ammonium acetate dissolved in water. Now, how do we calculate the pH of buffer solutions? This is a very important part. We have to derive the equation for pH for calculating the pH of buffer solutions. Let us start with an acidic buffer, which is a mixture of acetic acid and sodium acetate. The two equations which are happening in the aqueous solution are shown here. Now, we know that acetic acid being a weak acid having an equilibrium constant Ka, which can be written as the concentration of product upon the concentration of reactant, which is shown here. Now, you know that sodium acetate is a salt which has common ion. These are acetate ions which are common to the acetate ions in equation 1. So you know that the effect of common ion, what happens as the concentration of acetate ions in the above equilibrium increases, the equilibrium tends to move towards left hand side, giving you more of acetic acid and less of acetate ions. Also, the concentration of H3O plus would decrease because these two will combine to give you undissociated acetic acid. Okay, so addition of common ion will ultimately suppress the ionization of acetic acid. Right? So we say that due to the presence of common ion in solution, the ionization of acetic acid gets suppressed as per the Le-Chatelier's principle. Now, as a result, now we can assume that the equilibrium concentration of acetic acid in the solution would be same as the initial concentration of acetic acid added. Why is this so? Because we say that this acetic acid ionization is so much suppressed that the undissociated acetic acid equilibrium concentration would be absolutely same as the initial concentration of acetic acid. That means it has hardly dissociated into ions. So this assumption is true in the presence of a common ion. And we say that the acetate ions concentration at equilibrium can be assumed to be taken as equal to the concentration of salt initially added. This also holds true because the acetate ions coming from acetic acid are negligibly small. So whatever acetate ions are present in the solution, they are taken to be completely from the salt itself. So these two assumption is holding true in presence of common ion. Now replacing these assumptions in the equation for Ka, we can write that Ka is equals to sodium acetate, the initial concentration of the sodium acetate, which is equal to acetate ions, into H3O plus concentration divided by the initial concentration of the acid, which we have assumed to be equal to undissociated acetic acid. On rearranging this equation, we can write that the concentration of H3O plus ions is equal to Ka into the concentration of acetic acid upon the concentration of sodium acetate. Now, when we want to calculate pH, we have to take negative log of H3O plus. So we have to take negative log on both the sides and we get this equation. Minus log of H3O plus can be written as pH, and we can split this Ka and this ratio of acid to salt, and we can write down as log of x into y as log of x plus log of y. So we can here write minus log of Ka minus log of this ratio. And you know that minus log of Ka can also be written as pKa. So our equation becomes pH is equals to pKa plus log of salt upon log of acid. See, I have changed the sign of minus log here to plus log and reversed the numerator and denominator in the ratio. Okay, so here we can say conveniently that the equation for calculating the pH of a buffer is equal to pH, which is equals to pKa plus log of concentration of salt upon concentration of acid. And this equation is used to calculate the pH of the buffer solutions, and this is commonly called Henderson-Hasselbalch equation for the pH of buffer solutions. So this Henderson-Hasselbalch equation is very important equation from the numerical point of view, you will get the numericals for solving the pH of the buffer solution by using this equation. Now, similarly, we have just derived a Henderson-Hasselbalch equation for an acidic buffer whose pH is equal to pKa plus log of salt upon acid. In a similar way, we can derive the Henderson-Hasselbalch equation for a basic buffer, which says that POH is equals to pKb plus log of salt upon base. We can derive this equation in a similar way that we have derived from an acidic buffer. So once we know the pH of a basic buffer, POH of the basic buffer, we can calculate its pH by using the relation that pH plus POH is equals to pKw at 25 degrees for all aqueous solutions. So once we know the pH, we can calculate pH as pKw, that is 14 minus POH. Okay, so this was about the calculation of pH of buffer solutions. Now we have to understand how these buffer solutions does not allow any change in pH when strong acid or strong base is added to their solutions, how their pH remains the same. Now take for example acidic buffer solution, which is made up of acetic acid and sodium acetate. So we have the following equations that are taking place in the aqueous medium. Now just for convenience, let us write the undissociated acetic acid as HA and the dissociated acetate ions as A minus for convenience. Now I'll show you some pictorial representation of how the buffer resists the change in pH. Let us see this buffer solution, which has equal concentration of the acid as well as the salt. So we have HA, that is undissociated acetic acid in the solution, and A minus, which is the dissociated acetate ions. Now we will see what happens when a small amount of a strong acid is added to this buffer solution. Okay, when we add acid, let us say H plus ions from any source, it can be HCl or H2SO4. The moment H plus ions enter the solution, this will immediately take up these undissociated acetate ions and they will combine to give you undissociated acetic acid. Okay, and we can say this happens because of the Le-Chatelier's principle. The moment H plus ions are added externally from an external source, they will combine with acetate ions and make more of undissociated acetic acid. Now, due to this change in the equilibrium concentration, we say that as a result, the concentration of undissociated acetic acid would increase and the concentration of dissociated acetate ions or the salt would decrease. So decreasing the concentration of the salt and increasing the concentration of undissociated acetic acid is not going to change the pH of the solution. The pH of the solution would have changed if this H plus ions would have remained in the solution. But these H plus ions are not remaining as such in the solution. They are being combined with A minus, and as a result, the concentration of undissociated acetic acid are increasing and the dissociated ions are decreasing. So this is not going to change the pH of the solution. Okay, so this is how on addition of acid, there is no appreciable change in the pH of a buffer solution. Let us see in the same way if we add base to an acidic buffer solution. So we have an acidic buffer solution having equal concentration of the undissociated acid as well as the concentration of the salt. Okay, so what happens when we add a small amount of a strong base to this buffer solution? Now base, which is OH minus ions, will combine with the weak acid and gives rise to more of the dissociated ions and decrease the concentration of the undissociated acid. This can also be shown by Le-Chatelier's principle. If you look at the equilibrium here, although OH minus ions are not common to any of these ions in this equation, but addition of OH minus ions would try to combine these H plus ions, leading to the formation of water. And once these H3O plus ions are consumed by OH minus ions, the concentration of these H plus ions would decrease, and this will lead to the disturbance in equilibrium, and equilibrium will move towards the forward direction. And movement into the forward direction means the more acetic acid will get converted into acetate ions. Okay, so we say that acetate ions will have an increase in concentration, and the undissociated acetic acid will be decreased in concentration. So as a result of adding OH minus, we have decrease in concentration of undissociated acid and increase in the concentration of acetate ions. Again, there will be no appreciable change in pH. Why? Because the OH ions are not remaining as such into the solution. After combining, they are being converted into H2O. And the increase in concentration of A minus and decrease in concentration of HA will not affect the pH change appreciably. There will be no pH change on increasing or decreasing the concentration of A minus and HA. So we say that buffer resists the change in pH by absorbing the OH minus ions or H plus ions by their constituent ions present in the solution. Okay, now let us see what happens when we add acid to plain water, and what happens when we add acid to buffer solution. Let us compare the change in pH in both the cases. So this we have taken the case of water. Water, you know, has certain amount of H plus and OH minus ions, which is 10 raised to the power minus 7 at 25 degrees Celsius. And we take a buffer solution, which has equal concentration of the acid and the salt. Now, we will see what happens when a small amount of strong acid is added in both the solutions. When acid is added to water, it will immediately combine with the OH ions present in the water solution and gives rise to the neutral water molecule, thereby disturbing the equilibrium between H plus and OH minus ions. So as a result, you see there will be a decrease in the concentration of OH minus ions and an increase in the concentration of H plus ions. So we see addition of H plus ions has actually made appearance of H plus ions more and OH minus ions has decreased. So in a nutshell, we can say the concentration of H plus ions has increased in the solution, and due to the presence of naked H plus ions, the pH would increase sharply. However, in a buffer solution, when H plus ions are added, we have just seen this will not lead to any increase in concentration of H plus ions. However, it will only increase the concentration of the undissociated acid, and the concentration of undissociated acid will not going to affect the pH of the solution. Hence, the pH of the solution remains the same. Okay, so let us also calculate. We will see what happens when we add small amount of HCl to plain water. So let us take the case when 1 ml of 0.1 normal HCl is added to 1 liter of the plain water. What is the pH of water before addition? We know it is 7. What is the pH of water after addition? Let us calculate. We know that we have added HCl, which is 0.1 to 1 liter of water. So we can write the new concentration of HCl would be 0.1 into 1 upon total volume, that is 1001. That is giving you approximately 10 raised to the power minus 4 molar. So when we add 1 ml of 0.1 normal HCl in 1 liter of water, we say 1000 ml of water, the total volume has become 1001. So in 1 ml, it was 0.1 ml or 0.1 molar, and in 1001 ml, it will be 10 raised to the power minus 4 molar. So 10 raised to the power minus 4 molar HCl will have pH equal to 4. Now you see, on addition of 1 ml of 0.1 normal HCl to plain water, the pH has dropped from 7 to 4. So this is a sharp drop in pH. Okay, now let us see when we add the same amount of HCl into a buffer solution. Let us calculate. When 1 ml of 0.1 normal HCl is added to 1 liter of buffer, which is 0.1 molar in acetic acid and 0.1 molar in sodium acetate. We know that pKa of acetic acid is equal to 4.75. Now, we know that from the Henderson-Hasselbalch equation, when the concentration of salt and acid are equal, we say this is log of 1, and we know that log of 1 is 0. So pH will be equal to pKa, that is 4.75. Now, what happens when we add acid to this buffer? We have seen that on addition of acid, the concentration of salt would decrease and the concentration of acid would increase relatively with the same amount as the amount of HCl that has been added into the solution. So we will have to see how much salt has decreased and how much acid has increased. This will be equal to the amount of HCl added to the solution. So the initial amount of salt, we can calculate it by using Henderson-Hasselbalch equation by putting the value of pKa here, and then we also put the formula that amount of salt initially was n moles and the amount of HCl added would be the moles of HCl, and this will be subtracted from the number of moles of salt, and in case of acid it will be added. So you know that you can calculate the number of moles by, if you know the concentration and the volume, you can calculate the number of moles as m into v. We know that molarity is number of moles upon volume. So number of moles will be equal to molarity into volume. So what is the molarity of salt initially? We had 0.1 molar of sodium acetate in 1 liter of water. Okay, so this is 0.1 into 1 is the number of moles of salt present in 1 liter. And the amount of acid that we have added is 0.1 into 1 ml. So 1 ml can be written as 0.001 liters. So these are the number of moles of HCl added, which is subtracted from the initial concentration of the salt. And the same amount of acid has been added to the initial concentration of the acid. Okay, and after solving, we get that log of 0.1 minus 0.0001 and 0.1 plus 0.001. So we get log of 0.0999 upon 0.1001. On solving the log, we see that the net pH of this solution comes out to be 4.749, which is approximately equal to 4.75. So we see that there is no appreciable change in pH of the solution when 1 ml of 0.1 normal HCl is added to 1 liter of this buffer solution. And if we compare it with the change in pH of water, there is a sharp change in pH of water, as we have seen from 7 to 4 here. And here, there is hardly any change from 4.75 to 4.7491. Okay, so this is how we say that the pH resists the change in pH. And the buffer resists the change in pH. Okay. Now, what is a buffer range? It is observed that a buffer can resist. There is a limit for a buffer solution to resist the change in pH. How much acid you can add and till how much value of acid added, it can actually withhold the pH. There should be some limit beyond which the addition of more acid is not going to withhold the pH, right? So it is observed that a buffer can resist the change in pH till the ratio of the concentration of the salt to acid remains between either 10:1 or 1:10. That means either salt is 10 times that of the acid or acid is 10 times to that of the salt for any buffer to work in this range. Okay, beyond this ratio, we say that buffer loses its tendency to resist the pH change. And this defines our pH range as pKa plus 1 or minus 1. Okay, how we have derived this limit? pH, you know, according to Henderson-Hasselbalch equation, it is equal to pKa plus log of salt upon acid. So the lower limit can be found if we put the value of salt equal to 1 and acid equal to 10. So this will give us log 1 upon 10 is minus 1. So the limit is pKa minus 1. And the upper limit we can find if we can put the value of salt as 10 and acid as 1. So we can say this is pKa plus 1, and the buffer shows appreciable buffer action in the pH range where the pH is between pKa minus 1 or pKa plus 1. For example, the pKa for acetic acid is 4.75. That means the buffer range of acetic acid buffer would be 3.75 to 5.75. Beyond this range, the acetic acid buffer would not be able to show any buffer action. Now, what is buffer capacity? Buffer capacity is defined as the capacity to resist the change in pH. And mathematically, we can define buffer capacity as delta HA upon delta pH, which means it is a number of moles of acid required in 1 liter of the buffer to change the pH by 1 unit. How much acid can we add to change the pH by 1 unit? That is known as the buffer capacity. It has been observed that buffer capacity of a concentrated buffer is always more than the buffer capacity of a diluted buffer. And also, we have seen that buffer capacity of any buffer is maximum when the concentration of salt and acid are equal. That means when pH is equals to pKa, at this point, at this pH, the buffer has the maximum buffer capacity. Okay, and if we have, let us say the concentration of acid and salt is same for two solutions. In one solution, we have 1 molar solution of acid and 1 molar solution of salt. Let this be one buffer. And another buffer where the concentration of acid is 0.1 molar and salt is also 0.1 molar. So in both the cases, the pH will be same. However, the buffer capacity of the more concentrated, that is 1 molar buffer, would be more as compared to the diluted buffer. Let us do a numerical for understanding this buffer capacity. Calculate the pH of a buffer made by adding 1 molar of acetic acid and 1 molar of sodium acetate. Let us label this buffer as buffer A. Also calculate the pH of a buffer made by adding 0.1 molar of acetic acid and 0.1 molar of sodium acetate and label this as buffer B. Also calculate the change in pH when 1 ml of 0.1 molar acid, HCl is added to buffer A as well as to buffer B. So let us solve this problem in a stepwise manner. pH of buffer A would be equal to, according to Henderson-Hasselbalch equation, if we say the concentration of salt and acid are equal, so pH will be equal to pKa, that is 4.75. Similarly, the pH of buffer B can also be calculated as in the same way. If the concentration of salt and acid are equal, we can say pH is equals to pKa, that is 4.75. So both buffer A and buffer B has the same pH, that is 4.75. Now we will calculate what happens to the change in buffer in both the solution when acid is added. So we will take buffer A first. In buffer A, the amount of acid added we know is 1 ml and the concentration of HCl was 0.1 normal. And we can solve this by using the molarity and volume. The concentration of salt in the first buffer was 1 molar and we took 1 liter of this buffer. So 1 into 1 is the number of moles of salt and the number of moles of acid added would be 0.1 into 0.001. That is the volume of the HCl. 0.001 liters means 1 ml. Okay, so the initial amount of acetic acid would be again 1 into 1 because the molarity is 1 molar and the volume is 1 liter. And the amount of HCl that has been added is 0.1 into 0.001. So important thing to note here is when we added HCl into buffer A, which is an acidic buffer, the concentration of salt would decrease and the concentration of acid would increase. Okay, so we will solve this in a similar way that we have done before. We find that the pH comes out to be 4.74991. So pH of buffer A before adding HCl was 4.75, and after adding HCl, we have got 4.74991. Okay, now when we calculate the same for buffer B, we find that the change in pH is coming out to be 4.7491. For buffer A, it was 4.74991, and for buffer B, it is 4.7491. So you see that buffer A has actually shown a better buffer capacity. Buffer A can resist the change in pH more effectively than buffer B. Okay, so this is how we have derived that how a buffer capacity of a more concentrated buffer is higher. This is some of the problems for your practice. If you have any problems, you can discuss these. Okay, thank you.